So today we probably finished. We'll jump into chapter 7. Okay, so let me just give you a preview. We will jump into chapter 7. So that does not mean we finish chapter 5. Okay, you actually see I'll leave part of chapter 5 to later. So today is a combination of chapter 5 and chapter 7. So in chapter 7, we enter the focus is not analysis. So in chapter 5, it's about analysis. So in chapter 7, we start talking about design. And that's the more interesting part of this entire course. This entire course is much about filter design. Okay, so you'll be able to learn how to design some kind of a system that gives you some kind of desired frequency response. Either low pass filter, high pass filter, things like that. So today we'll formally, hopefully, this week is not today, but this week we'll start we're entering this area of design, filter design. Okay, so that's for this week. And so in particular, let's try to recap from last time. So last time, in the end, we talked about the decomposition, right? So does anybody remember what the decomposition called? It's called APMP, all-path mean phase decomposition, right? So we argue that any stable system, this system can have some poles and some zeros. And for a system to be stable, we're sure that all the poles have to be inside the unit circle. And how about the zeros? If all the zeros are also inside the unit circle, that was the topic we were talking about last week. So if all the poles and zeros are both inside the unit circle, we call the system, this kind of system has a name, right? So we hope you remember that the name is minimum phase system, right? And we argue that for any minimum phase system, we can construct a stable inverse, stable causal inverse. So that's kind of one cool property, good property of the minimum phase system. And the last time, we said if all the poles and zeros, let me just draw all of them for them. Okay? If all the poles and zeros are inside the unit circle, this kind of system is a minimum phase system. But for everything else, we said it so happens that some of the zeros are outside the unit circle. Let's say, for example, let's say we have 1 0 outside. Okay? If we have 1 0 outside, then what we can do, then this kind of system cannot be converted. I mean, if we really construct the inverse, that system is not going to be stable. Okay? So we cannot find stable causal inverse for any system that has a 0 outside. So what we can do instead is to find a virtual location right here, so that the radius, the distance to the origin has to be relation. Okay? The distances to the origin had to be reciprocal. 互为导数 reciprocal. Let me just reciprocal. So if a system has a 0 outside, then what we can do is to find the reciprocal location now inside the unit circle and do something there. And the thing that we do there is to create virtually a pole and a 0 on top of each other. Okay? So at this reciprocal location, we will create a pole and a 0 on top of each other. Let's say we have a pole and a 0. So they actually cancel out. And according to my color, so my color right here suggests that the green goes with the green. Okay? So we'll pair up this virtual pole with the outside 0. And then leave the virtual 0 inside. Okay? Leave the virtual 0 inside to combine with everything else. So the system now is decomposed into Now the system is decomposed into, so now this system is no longer minimum phase. But now we can decompose it into the product of a minimum phase system having one virtual zero inside two poles, so this particular example, 2 zeros. That's a minimum phase system times the inner frequency response. Okay, so this is h of min in the D domain, if you will. Let's say this is h of D. Any arbitrary f h of D that is stable and that is not necessarily that is stable and constant. Okay, can be written as the product of minimum phase system times the all-pass system. And where does the all-pass system come from? The all-pass system is there because of this pair, but outside zero is the virtual pole at the reciprocal location. So reciprocal means that if the distance to the outside zero is r, then distance to the inside this pole inside is 1 over r. Reciprocal locations. 互为导数的Alright? So, and this system, we know that since the distances are reciprocal, this system is going to be all-pass. Meaning that magnitude response, we can make it adjust the scaling factor so that magnitude response is constant 1. It's a constant. Every frequency receives the same gain, which is unity gain 1. Okay? So h of all-pass. So e to the j omega such that the gain is unity for all frequencies. Any questions so far? That's what we were at last time. So last time I also raised the question, why? Why is this property referred to as minimum phase? The property of having all the zeros and poles inside the interval. Why should we call it a minimum phase system? And I think that's a totally valid question, right? So this is kind of my sharing. Whenever we learn something, learn a new terminology, you should, I would invite you to think about why people call it that way. Right? Why isn't it a maximum phase system? What is it, in what sense? In what from what angle can we why do we call it minimum phase? What kind of phase is becoming minimum? Okay? So the answer is now actually the minimum phase system has 3 properties that I want to share with you. Properties of the minimum phase system. Property of minimum phase systems. Okay? And 3 properties. The first property is that the reason why we call it minimum phase. The first property really is if we look at this if we look at the angle, the phase response of this system, we know that the phase response, since now we have a decomposition, okay, since HD is H mean times, you know what I mean, okay? So the result is, let me just, since H now is decomposed into the product of 2 things in the complex domain, and we can just take the phase response. Take the phase response. The phase should be the addition. Multiplication in the complex domain becomes addition after you take the phase. Okay? The phase part. So the angle part, the phase response becomes the summation of the phase response for the minimum phase part and the phase response of the all-pass part. And further, if we just unwrap the phase, remember that there's the issue of unwrapping, so let's not worry about it too much. Assuming that these angles are after unwrapping. Okay, after unwrapping, then we can take the first derivative. Right? We take the first derivative and then taking the first derivative with respect to omega, then we have the result is we get this result. The group delay of the original system. The group delay of the original system as a function of omega right here. Okay. is this notation okay for everybody? The group delay of this system as a function of omega. Okay, that's the way I read it. Okay. This group delay is also becoming the sum of the respective group delay of the decomposed systems. The mean part as a function of zero plus the group delay of the all-pass part. And in your today homework is due, right? So in that homework, I hope you have worked out and convinced yourself that the group delay for any all-pass system at every frequency is going to be never negative, right? So that's our homework. So we use this result since this part is always greater than or equal to at least zero. So we get the conclusion. Any system, for any system, the group delay at every frequency is greater than the group delay of its minimum phase part. For every frequency, okay? And this is a reason why this system is referred to as minimum phase, because something is minimum among all other choices. Okay, something is minimum. But let's say if we know the how do I say? What's the good way to express this? Anyway, this is a property, regardless. And we know that something this group delay is the minimum among everything that has the same magnitude response. Let me say that again. This system has the minimum group delay at every frequency among all systems that have the same magnitude response. Okay, because any other system, if it's not equal to this system, the group delay is longer, never shorter, right, at every frequency. So that's why we can tell, so from another way to put it, another way to say it is that we just simply say, oh, this kind of system which has all the zeros and poles inside the unit circle, then we reach a conclusion that its phase from its group delay is going to be the shortest among all other systems that have the same magnitude response. Okay. So that's a property, okay? And today we keep looking at two more properties. The second property I will simply state it without any proof, okay? Because the proof is actually one of the assigned exercise problem at the end of the chapter. So I'll just point it out. The second property is a minimum energy delay property. And let me just give you a preview. The third property is uniqueness. Now, what does that mean? I will just share with you shortly. Okay? The third property is what I call uniqueness. Okay? So let's look at the second property first. The minimum energy delay property. What does that mean? That means, let me put a few conditions first. If h of n is the impulse response, okay, h of n is the impulse response of the system. And if h of n causal is causal and stable. And h and h is some frequency response if it is now decomposed into the minimum phase part times the all-pass part. Okay, and the way to do it is through this very simple procedure. Okay, we have a system, its impulse response is h of n, and now the system in the frequency domain can be decomposed into minimum phase and all-pass as we have introduced to you using that method. And let's say assume that the minimum phase, we'll just keep using our notation. Okay, our notation is assume that is inverse Fourier transform is H min, is denoted as H min of n. The corresponding impulse response for this interface system, okay? You can always calculate that. Always calculate that, right? So now we have two things. One is the impulse response of any Calvin stable system. It's impulse response to a difference equation. Okay, it responds to a difference equation Calvin stable. And now, by going to the frequency domain, we can make the decomposition and then come back to the time domain. That's the idea. Okay, we start with the system, go to the frequency, the impulse response, go to the frequency domain, and figure out the minimum phase part. And then for this minimum phase part, we also try to get back to the time domain. Now we have two time domain impulse responses. Okay, any questions so far? And there will be a kind of inequality kind of relation between H and H min and n, which I'm going to introduce to you. So then, I'm using that, note that now we know that the magnitude response is going to be equal at all frequencies, right? Because all paths is all paths. Because all paths is all paths, the magnitude response equals after this composition, right? Therefore, hope this is not too surprising. Let me say summation. Then the energy, I'm going to show you right now that the energy, the sum of square, okay? The sum of square in the time domain for H n equal to the sum of square of H min. And I'll just write down. If you sum up from 0 to infinity, okay, this is a causal system. H of n square actually will be equal to that of H min. The sum still n from 0 to infinity. H min of n square, sum of square, and that's a relation. And we're not done yet, but why? Any question right here? Do you understand why this relation has to hold? Do you understand why this relation has to hold? Now we have note that. Note that. Please note that. Please. Actually, please. Please note that. We have equal magnitude response at every frequency, but why? Can anybody tell me why there's a therefore? Therefore, the sum square is possible theorem. Okay. Oh, sorry. Quick question. Thank you. Let's put n okay. 谢谢。好。Okay. But this is thanks for sharing. This is as a result, as a consequence of Parseval's theorem. Parseval's theorem states that the energy can be calculated in the time domain as well as in the frequency domain. Right? But how do we calculate energy in the frequency domain? Didn't we do what we did was to integrate the square of this thing, right, over all frequency. And the reason is Parseval's theorem. This is because of Parseval's theorem, which states that for any system, the there should be 1 over 2 pi. Okay, but anyway, from -5 to pi, we integrate the power spectrum. You integrate the power spectrum over all frequency and divide that by 2 pi. It can actually give us the total energy in time. Same thing. Because of this theorem, and I'll let you figure out the detail. Okay, so this is a consequence. It's a consequence. As a consequence of Parseval's theorem, this relation has to hold. Now the two things here, H of n and H min of n, have the same total energy. That's another way to put it. They have the same total energy. because one of them is simply the whole path minimum phase decomposition for the other one. Okay? Any questions so far? So that's not that hard, but what is surprising, and it takes a lot of work to actually prove this following property. Let's call this the property subproperty 1. Okay? Subproperty 2, 第二个子项目 subproperty 2. If we just sum, so now this is a note that this is a sum from 0 to infinity. Okay? I will assume the system is positive, so we can ignore the negative time part. Okay? So that's why this summation index starts at 0. Okay? So that should be probably the second part is quite surprising. What if we take the partial sum? This is a limit to infinity, right? But what if we stop at time big N? Take the partial sum from 0, 1, 2, 3, all the way to n minus 1, big N. Is there a relation? The answer is yes. There's an inequality. That's the partial sum. When we sum up n, okay, n. Let me just say n. N from 0, let's say to a big N. Okay, partial sum. Same thing. We take the partial sum, and surprisingly, for any, if we stop calculating the sum at time n, big N, then this partial sum is going to be smaller than 0 to similarly at the same time h min. And this is kind of an interesting property in parallel to our previous property. Okay? This system not only has a minimum group delay, but also when we talk about the energy delay property, we calculate energy from time 0 to the time big N. Then if we stop, and for any stopping time N, we look at the partial sum, we found that the minimum phase part has the largest sum, even though the infinity they approach the same total energy. Okay? But the partial energy, if we stop counting at time N, the minimum phase system has the most energy concentration toward early time. Is that clear? It has its energy distribution is more concentrated toward early rather than later. That's the meaning. Let me draw a picture. Okay, what's the meaning? What's the kind of, how do we interpret this? How do we picture this? So let me just share with you. The way I picture this is that now we have maybe some kind of h of n, okay? Which can be positive or negative, right? H of n. And the response can last forever. Fine. But now after this procedure, we perform all pass minimum phase decomposition and find out the minimum phase part and its corresponding input sum. It becomes another function, h min of n, right? But this h min of n, we find that the total energy is going to be the same as h of n. But the partial energy, you would expect the total energy to be the same, but the partial energy, maybe it's more concentrated in earlier time, but the total sum of squares are equal. And this is referred to as the minimum energy delay property. So that's the way I see it by kind of drawing an example. Any question, any comments so far? Anything that is not clear? And I'll just skip the proof. We don't have so much time. If you're interested, work out problem 5 or find the answer. Okay. Problem 572. There is actually an exercise which guides you through the proof. It's pretty tricky. It's a very tricky proof. Any comment here? Except this part. This is quite challenging. Draw 3 hammers. Very challenging. Very challenging problem. Okay, so that's the second property. And the third property, let me just jump to it. The third property, I call it uniqueness. uniqueness. Unique level. Unique level. I just bought this plant from Uniqlo. That's English inside. My new pair of pants. Uniqueness. And this is about spectral factorization. 在题目上面做这种再做分析 spectral factorization. Okay, so the idea is that for a minimum phase system, if you know the magnitude response, then you essentially can calculate its phase response. And that's quite counterintuitive. Let me say that again. For any minimum phase system, other than stable minimum phase system, if you're given the magnitude response, then you can calculate the phase response. The phase response is inferred from magnitude response. Which is essentially the phase response will be uniquely determined if you're given the magnitude response. And that's quite surprising. That is indeed quite surprising. It is surprising. That's surprising. Okay. For any minimum phase system, if I tell you what the magnitude response is, then you can tell me what the phase response is. That's quite surprising. Right? Because we tend to think about, okay, the complex number, right? You can have a magnitude response and you can have a phase response. They are not necessarily correlated. They're not necessarily related in any regard. But for this special case of minimum phase system, essentially the phase response is determined from the magnitude response up to just a constant phase change, phase difference. And that could be surprising. One of them is determined by the other. Now it is surprising. Okay, thank you. It's surprising. Okay, so let me just write down. If H min Ej omega, okay, well, let me say H min Z, maybe more H. If all the, let me just say if H min is a minimum phase system, okay, if H min Z is the system function of a minimum phase system. Of a minimum phase system. And we know that by definition, that means all the zeros and poles are inside the circle. I'm going to use it, okay, use this definition. So this, actually this can be, so yeah, the property goes, if H min is actually referred to a minimum phase system, then how do I say it? Let me say not that if, let's say assume that, okay? Assume that this is a minimum phase system. Then if, let's say if we know the magnitude response, if the magnitude response, and for this case, let's denote the magnitude response as R of omega, okay, R of omega, which means the magnitude response. If the magnitude response is given, is known, if we know the magnitude response, then we can calculate the phase response. We can calculate theta of omega that is defined as the phase response. Then essentially, phase response can be derived, can somehow derived from the magnitude response without knowing the actual. If we only know the magnitude, we know the phase at every frequency. And that's somehow that's the surprising part. Then we can calculate this, okay? And or should I say we can determine, let me apologize for keep changing the wording. Then we can determine this phase response, should I say essentially uniquely. So by essential, I mean that, yeah, you can calculate the response. But for any other system that has a constant phase difference from the system that we determine is also valid solution. We'll see in a moment. Okay, so we say essentially, but essentially you can calculate phase response based on the magnitude response, and that's the surprising part. And that's a property for a mean phase system I'd like to share with you. Any question here? Any question here? So that is to say, if we're given the magnitude response, okay, let's say the magnitude response is has a peak, and we have a dip, and something like that. This is the magnitude response, for example. If we're only given a magnitude response, then we can actually determine the phase response. They are interdependent. Then the phase response can be, you can draw the phase response, something, okay? That's the idea, determining the phase response from the magnitude response. And why is this so? What's so special about the minimum phase system? So I'll give you a sketch of proof. Sketch of proof. And this proof requires some concept about complex analysis. We'll touch base on some concepts. If this sounds too unfamiliar to you, please just feel free to ignore. I'm not going to test you on this. Okay? I'd like to share with you. If you have a foundation in complex analysis, undergraduate in engineering math, then I'm going to give you a sketch of proof. The key point, let me use this board. Okay? The key point is to note that since for a minimum phase system, all the zeros and poles are inside the unit circle, right? Because all the zeros and poles are inside the unit circle, nothing's outside. Okay, nothing's outside. Then now consider taking the complex logarithm. How many of you have learned how to take the complex log? For a complex number, you can also take the log. Remember that. Which you are from the double department, you should have done that as undergrad. Okay. So now consider, for better for worse, let's consider taking the log of this system function. Log of h of z. Log of h of z consists of the log of the magnitude h of z plus j times theta of z. By definition, that's the definition, okay? In other words, the magnitude response and the phase response are the real part and the imaginary part respectively of what? Of log of h. Is that all right for everybody? I want to pause a bit. I want to pause that this relation is kind of fundamental. Okay? Taking the complex log, and the reason is because h of z by definition is the magnitude response times e to the j, the phase response, right? Therefore, we take the log, at least symbolically. Taking the log, the real part becomes log h z, taking absolute value plus e to the j theta taking log, e is gone. And now we are left with j theta, right? That's fine. Okay? That's fine. So in the rest of the program, we're going to consider, we're going to begin taking the log of h of z. Taking the log of h of z, and it has to be a part and an actual part. Okay? So let me just move here. First step, log. Taking the log of h of z, we have is equal to log of hz absolute value plus j log No. J1. J is theta of Z. J is theta of Z. It's raining outside. Okay, J is theta of Z. And the second step, okay. Now, log of h of z is a complex, a function of complex variable, right? Log of h of z itself is a function of a complex variable, log of h of z. So let me ask the question, where are the singularities? Where singularity 基点知道吗？ Singular, where are its singularities? The singularities are at where? Where are these singularities? Where can we not evaluate log of h of z? That's the meaning of singularity. You cannot evaluate the function, the size of the functions. 就是奇异点啊，不能。Now recently, black hole has been a big news, right? Black hole is kind of a singularity of the space and time, okay? But you cannot evaluate it. But here, in complex analysis, singularity means that the places where you cannot evaluate the function. And let me ask, where are the places? The singularities has two possibilities. One, where when the original h of z has a pole, there h of z is already not evaluable. For the pole places, you cannot evaluate h of z. Therefore, you cannot evaluate log of h. Okay? Also, similarly for the zeros, h of z equal to 0 by definition, right? What is log of 0? You cannot evaluate log of 0. So the answer is, if you ask the question, where are the singularities? The answer is the two places with poles and zeros. Okay? So, second thing to note that the places, the poles and the zeros, these places are singularities. Indeed, you cannot evaluate log of h of z over there. Singularities. And we know that by definition, they are all these singularities for log of h of z are inside the unit circle. Okay? All of them are inside the unit circle, which are all inside the unit circle. All inside the unit circle. So in other words, 2 prime. Okay? In other words, if all the singularity, this is now why the idea of complex analysis comes in. Okay? If we have a complex value function which are singular only, which could go singular only inside the unit circle, then that means outside the unit circle, everywhere the function is analytic. Analyticity, okay? Therefore, in other words, how should I say? Now, let me say therefore. Therefore, at z greater than 1, an open region, this open region z greater than 1, outside the unit circle, this log of h of z function is analytic everywhere. Log of h of z is analytic everywhere. Analytic everywhere, okay? All right, so if that happens, we know that if a complex value function is analytic somewhere, it means that the real part and the imaginary part has to satisfy a relation that is called the Riemann-Cauchy equation. Does that ring the bell? 你用机器的印象。Riemann-Cauchy equation, okay? actually two results, Riemann Cauchy. Now let's denote the real part imaginary are u and v. Okay, easier this way. Let's denote log of hd as u of v plus I times. So we've been using j, right? Let me just keep using j. J d v. Real part, imaginary part. Because this log of h is analytic everywhere, analyticity, 可解析性, has a lot of good consequences. First of all, you can calculate its differential. Does that ring the bell? 你们激起你的想法吗? An analytic complex function is differentiable. Its first derivative exists with respect to z. And secondly, the real part, the imaginary part, satisfies this Cauchy-Riemann equation. Cauchy-Riemann, really not Riemann-Cauchy. Cauchy-Riemann. Cauchy-Riemann function. If we denote the real part and imaginary part as u and v respectively, then we know that because of analyticity, 因为这个可解析性 analyticity, say that analyticity. Repeat that to me. Analyticity. Good word. Okay. Because of analyticity, we have the consequence that partial u, and let's say z equals x plus iy, okay, as usual, jy. Then we have this relation. I hope that it starts to give you some. I hope you have some learn this. Then we have these two relations that are kind of symmetric. And partial v, partial x equals to minus partial u, partial y. That's the Cauchy-Riemann relation. That's the Cauchy-Riemann relation. Okay? Now some people are nodding. So you might have learned it. You might not. But let me give you a example. Then further, because this analyticity, we know the real part and the imaginary part, you can determine the imaginary part given the real part. Both of them. So they are called, in complex math, they are called conjugate functions. Okay? Not complex conjugate functions. Kind of confused. But the important thing is that you can, two things. First, actually this is a hint that you can determine v from u, or you can determine u from v, vice versa. They are not like totally independent anymore. Okay, they're related, they're highly related by this. They're closely related by the Cauchy-Riemann relation, Cauchy-Riemann function. So the idea now is becoming more clear that you can determine. Because of this interdependence, you can determine v from u, in particular, vz from uz. How exactly that can be done is referred to complex analysis. Okay? So now we are reaching a conclusion. Therefore, when we look at this, vz is the imaginary part, uz is the real part for any z outside the unit circle, okay? Any z outside the unit circle. But let me insert one more point because to be more rigorous. Not only can you determine v from uz, but also u and v respectively, each of them satisfy the Laplace equation. The Laplace equation. But also, we say u is a function of z, therefore u is a function, you consider that as a function of x and y. Now we have, both u and v have to satisfy this partial differential equation. And it's not hard to verify. At any point outside the unit circle, okay? So any point outside the unit circle, we know that u and v will both satisfy the Laplace equation. Laplace equation. This is a Laplace equation. Okay, so here is now finally I've collected enough information. I want to show you how you can construct the phase response given the magnitude response. Okay, I'm going to show you in a moment. Then, collecting these background knowledge, then I'm going to suggest how do we, because we're trying to talk about uniqueness, right? That for a minimum phase system, the phase response can be determined from the magnitude response. And so I'm going to show you how to do that next. Okay, ready? So now finally, note that you're given h of e to the j omega is r of omega. That's a boundary condition. That's actually the boundary condition for for u of xy. So what else do we have here? Now we have the unit circle still there, okay? And you are given the magnitude response. By giving you, by specifying the magnitude response, we actually specify a boundary condition on the xy plane for u of xy. It's a boundary value problem and extending to the outside. Okay, so you're given the boundary, like here on the boundary, on this unit circle, u of xy is equal to r of omega, where omega is this angle. Okay? You're given this boundary condition, and I've convinced you that outside, everywhere, you satisfy the Laplace equation. And we know that the Laplace equation, for the Laplace equation, solution is unique. Given the boundary condition, that's another piece of knowledge from partial differential equation. For the Laplace equation, given the boundary condition, and solving the partial differential equation, the solution is unique. You can solve it uniquely. Okay? So that is given r omega, we can solve. Finally, given r omega, we can always solve u of x and y at outside the unit circle. It's always doable. How to do that? This is a standard partial differential equation. This separation of variable. It's so really Fourier transform. Okay. Separation of variable. So you can solve it by separation of variable. It's doable. It can be uniquely determined. But once we uniquely determine u of xy, and we say we determine it uniquely. Uniquely. Once we get u of xy used, then we can use the Cauchy-Riemann relation, to obtain v of xy over the same region, which is outside the unit circle, everywhere and everywhere, because of the Cauchy-Riemann relation. Is that okay? Okay, everybody. You can then using the Cauchy-Riemann equation, you can determine v of xy can be determined. And it's actually equal to a particular solution plus to a constant. Okay, there may be a constant difference, but that's not important. Uniquely, you can just if you're given u of xy, then from here we can determine v of xy, okay, up to a constant difference. And the final step involves And this is defined over for any for outside unit circle. Okay? So now, if for the outside unit circle you can determine v of xy, now you can calculate that, then you just take the function, just approach it to the unit circle. Take the limit toward the unit circle. Because outside everywhere we can determine v of xy, right? So just imagine, you can imagine that when the radius approaches 1, on the boundary you can also solve v of xy. Okay? So taking the limit z approach 1 of v of z, then we can solve the imaginary part, and that will be our beloved theta of omega. That's the idea. That's kind of the derivation in a nutshell. Okay? Because what is v? V is the imaginary part, right? V is the imaginary part of log of h. Now, what is the imaginary part of log of h? That's phase response. So basically, v and theta here are the same thing. So, yeah, I'll just take a break here. Think about this. These are the two steps. Kind of, in a nutshell, how do we convince ourselves that really, for a minimum phase system, because all the zeros and poles are inside the unit circle, therefore all the singularities log of h are inside the unit circle. Therefore, the outside is entirely analytic. Therefore, the real part and imaginary part are not independent, essentially. And what are the magnitude response and phase response? The magnitude response, so this part is u, and that part is z. So they are not independent. You can determine one from the other. Okay? So that's kind of briefly how that works. So take a 10-minute break. Please turn in the homework. Okay, so why should we care for a minimum phase system? The magnitude response determines the phase response. Let me try to think why this could be important. Okay, it's not. But I was trying to think. Yeah, so there's in optics, in the field of optics, function. So we have optical materials. 光学材料。 Let's say we have a piece of optical material, and actually these magnitude and phase responses are meaningful. Physically, they have meanings. So for example, for a piece of optical materials, maybe the magnitude response. The magnitude response tells us how much how much the light is attenuated or absorbed in the material per unit distance. Now, okay, then you can characterize, you measure the optical property for a piece of material. How much, let's say, optical fiber, right? You care about how much the light is attenuated over 1 kilometer per distance, per unit distance, right? So that's like the magnitude response for this material, for light, at the frequency of light, in the wavelength, high frequency, electromagnetic wave, okay? So the real part, in that case, for example, for this optical material, the real part, let's say we have a piece of something, that is so long, right? And we can investigate, we input, let's say x of t, because this light is continuous time, very similar. The output, measure the light in its spectrum. We also take the Fourier transform and measure the spectrum, right? Measure the spectrum, y and j omega. And this system is a linear. This is a linear system, and we can characterize it with a system function h of let's say not anyway. So let me say just I put everything in continuous time. Okay, so j big omega. So this could tell you how much the light is absorbed or attenuated from from the left side to the right hand side. Okay, so we say this is attenuation. As a function of frequency, every frequency would go through this piece of fiber with different ratios of attenuation. Some light have, for example, red light versus purple light, right? We know that in the air with some water, which light attenuates more? Is it purple or the red? Why do we see a red light? Why the red light has to be a red light? Because it needs to penetrate the air at a longer distance and as long as possible, right? So H of Z really, in the field of optics, H of Z, the magnitude tells you the attenuation of gain. The traveling gain from one point to another point. Okay, so it's meaningful. And how about the phase? The phase response. The phase response. The phase response has something to do with. Let me just prove. The phase response. The phase response tells you from point A to point B, how much of phase accumulation would happen for every frequency. In other words, it tells you the wavelength or the refractional index as a function of frequency. 折射率，这个跟折射率是有关的 ，because it tells you how much phase accumulation per unit distance with the light experience, right? So 相角差嘛 phase difference, right? 相角差。The phase difference is related to wavelength. Is related to wavelength of omega. Or there is the concept of refractional index. 折射率. Yeah, I mean, like if. For example, if lambda is simply speed of light divided by frequency, there might be 2 pi somewhere. So that's not very important. It should be 2 pi. Okay. So that's one possible relation. Lambda is totally just the inverse of omega, inversely proportional to omega. So that's one property. We know that for this example, every light at every wavelength travels at the same speed. Right? There's no dispersion, there's no suicide, there's no rainbow. But for everything else, so this is a constant. Oh, this is not constant. Anyway, you know what I mean. But if C is the function of frequency, then so. Essentially, it relates to, I'm trying to point out that this phase response has something to do with the speed of travel. Okay? So it has something to do with the refractional index. Okay? So the property of minimum phase is a serious issue that we can discuss if a piece of optical material is minimum phase or not. Because if it is minimum phase, then we have a nice property that actually the attenuation spectrum determines the refraction of vice versa. They are not independent. They're not independent. So the reason why, so you can say the reason why this particular frequency, particular kind of color of light cannot penetrate is because the real part and imaginary part are not. I'm just trying to say this is not right. Attenuation and refractional index could be related for a piece of material. Like if the material satisfies our minimum phase property. In the field of optics, I'm very interested. This relation sometimes is called the Kramernick relation. The real part and the imaginary part of the propagation, what should I say, propagation function? The real part and imaginary part of the wave number function. Okay. The wave number function, k of omega, has a real part, let's say, mu of omega plus j times nu of omega. And one of them is a wave number, the other is attenuation. Okay? And the sum, the complex sum, is called, we call it a wave number function. The real part, imaginary part, are not independent. In the field of optics, we can discuss issues like this. Right? But now we are back to digital signal processing. So this is just to share with you a bit of more concept in different fields that are actually closely related, intimately related to Qinyi and Guanxi, intimately related to the concept I introduced in this class. Okay? Any comments here before we move on? So those are the three properties I would like to share with you. Three properties for mean phase coverage. The first property, the group delay, really is the minimum among all systems that share the same magnitude response. Second property that we just erased. Second property, that the energy delay property, that the energy delay for the minimum phase system is more concentrated toward earlier time rather than later. While the total sum of energy and impulse response are equal. Okay? That's the second property. And third property is that you can, for a minimum phase system, surprisingly, you can determine the phase response from the log of magnitude response, because both of them will satisfy the Cauchy limit relation outside the unit circle. Okay? Two properties.